Now we leave the time domain and look into the frequency domain. Yeah, that is the next step, 3.2. Why this is called frequency domain? Because our variable is not anymore the time, but will be now the frequency. The way to convert the signals from the time domain into the frequency domain is going via Laplace transformation. Yeah? The Laplace transformation is a mathematical procedure which is rather complicated. Yeah? We call this with a big L function. The writing could be in this way. If we have Laplace transformation procedure, we can call this with a large German L with parentheses, and this is a time function. And now we want to convert this with the following function. This is an integration over this function, and we multiply now this function with the exponential function, and in the exponent of the exponential function we have now a negative p times t. T is the time, but p is a new parameter, it's a complex frequency, and we integrate over the time. And that is important. Now the definition starts with 0, goes to infinity. Yeah, we have an integration, not a general integration, but an integration within limits. And you know, if we integrate over time and then set the limits from 0 to infinity, then the parameter t disappears. We have then only a function of p. New parameter is p, the complex frequency p, complex frequency. It's not a real value, but that is the not so easy to understand method. We have a real part plus j omega. That is the radian frequency, and this is a real part. And please forgive me that we now have the same Greek letter for a total different information. That is common in literature. I cannot change it. I will use this, but because this is so totally different, this real part of the complex frequency, that there could be no mix-up of the unit step function. Yeah, they are so different that we have no problem to work with the same letter with two different meanings. Note that in English literature and US literature, they prefer to use the complex frequency S. In USA, they use letter S. I don't like it because very often we have functions like in a PT1, we will learn it in this chapter. In a PT1, we have transfer functions which can be written in the way 1 divided by 1 plus, say, 0.2 seconds, time constant, times complex frequency. In USA, this will be written in f of s is 1 divided by 1 plus, and now we have the problem, the time constant is second, and then they use the unit SEC times s to differentiate between seconds and seconds. Yeah, s complex frequency second. In German, for the time unit we use an s, and imagine complex frequency is s and time unit is s. Then how can you differentiate between the second and the complex frequency as that is impossible. Yeah, so here very important. Yeah, this is use A, or MATLAB, use complex frequency as but in this lecture we use the p value. I think it's not so difficult to switch between complex frequency S and complex frequency p letter. Okay, back to the Laplace transformation. This solution for special functions is rather time consuming, but if we have a solution for one special function, this solution can be used for the next time with the result. So I have only to solve this integration one time in life, then I can use the result for my calculations for the next years and decades. Yeah, and mathematical scientists like to solve this type of integration. An engineer don't like it. Yeah, so I have, I think, one time going through this integration for the step function. It's time consuming. I leave this calculation areas to mathematical specialists. So we have a list of functions which are converted into the frequency domain, and this list is called Laplace table. Yeah. So the solution of Laplace conversions is done for millions of functions. You can find in the internet big tables from any university has a table in its internet presentation. So we have just to work with these tables in a good way. Yeah. To avoid this strange writing, German L with these parentheses, avoid writing of this integration, we have a symbolism which is rather easy. Here this f of t ends up in a new function, and I call this f of p. We would like to use for time functions lowercase letters. For I have mentioned this, and for frequency functions uppercase letters if possible. Sometimes this is not possible, then we have to live with this. And these both functions corresponds over this integration, and this can be written in the following way. Symbolism. I like the symbol. F of t belongs via Laplace transformation to the frequency function f of p, and the symbol is an open circle here and a black circle there. That means the frequency side is filled with black color, the time side is then open. This symbol gives the information that f of t and f of p belongs together via Laplace transformation. If I have an f of p, the question is, can I then reconvert it into f of t? Yes, you can. That is the inverse Laplace transformation, a similar integration. I don't write it down because we have heard it in mathematical lectures. If we convert one function into f of t into f of p and then reconvert it with the inverse Laplace transformation, then we get the same function. So the way from left to right and right to left is gives the same result. So we have a reversible function. Or in other words, the information which is containing in f of t is absolutely the same as in the f of p. So there is no information loss caused by this integration. That's important. F of p contains the same information as f of t. That is the way to use it. The problem comes later if we discuss graphical display, and so then you will see we and the beginner, and you, I think, the same, has problems to understand the function f of p. Yeah? Our brain refused understanding what is an f of p. So we have to work with this. The reason why we like to do this in frequency domain comes now. Because the mathematical procedures in frequency domain are much more easier than in time domain. But first I want to give you some examples, and then we look into one Laplace table. Yeah? if we convert the sigma, the unit step function, into frequency, unit step function, then we get the very simple expression, which is 1 over p. It's a unit step function. If we do this with the delta impulse, the conversion is much more easier. It's the most easiest transformation, because then we have a 1 in frequency, constant 1. If we, for example, have a ramp, if we have a t and convert it, this gives then a 1 over p squared. It's a ramp function. What is a ramp function? Just ramp function is 0 up to this point, then constant increase ramp of t over t. And this ramp function is converted in 1 over p squared. We will use this later in some examples, I think. You can find much more information, many more terms in a table in workbook. The pages 9 to 11. Let's have a quick look into these tables. On page 9 you can find the first part of the 3 pages table I have presented for you in my workbook. You can use this table in examinations. So I show you some characteristic of this table. The internet is filled with similar tables, but my table has 3 columns. Here the left column is an indicator. This is the frequency function, and this is the time function. Note the time functions are 0 for negative times. They all start with t0. It's not especially written here. That is just a characteristic of the Laplace transformation, because the integration starts at 0 and we assume 0 initial conditions. Frequency function with p, and here note the row indicator has 2 digits and then a letter. The 2 digits are just degree information of the numerator. The second digit is a degree of the denominator. So in the frequency function, look here, this function has a constant value here, 0 degree numerator, and a p to the power of 2 second order function in the denominator. So here is a c, and if we have the same letters, the same digits here, we have a letter A, B, C, D on the third part of this indicator. So here you can find very easily, if you know my frequency function has first order here, second order there. I look into the section of this table which starts with 1.2. It's a way to quickly find good expressions. Here you see delta impulse 1, unit step function is 1 over p. Here's the ramp, 1 over p, and many other things we will use later in some training examples, how to work with this table. Okay. Now I show you why we prefer to work in frequency domain in chapter 3.3. We use the frequency domain for the calculation of system responses. That is the reason why we go into the frequency domain. So assume we have the following system: 1 input, 1 output. This is xe, this is xo. Maybe we know the dynamical behavior with in the form of the differential equation, and now we want to solve this differential equation for a special input signal. to get the output signal. Now the goal is I want to calculate mathematically the response of a system on any input signal. Then I have to solve the differential equation. As I have mentioned, the solution, manual solution, is very time consuming, difficult, and sometimes not possible. The solution of a differential equation is used in simulation programs. Yeah, in my simulation program like C#, for example, the differential equation is used to step-by-step calculate a solution. So for numerical programs, this can be done, but manually, if you want to have equations, this is very time-consuming. The way is now very simple. You see here, you can say this is a time domain. We go now into the frequency domain. First step is we convert the input signal into a frequency signal using, for example, the table, or if this is not available in the table, looking for other tables, or if you cannot find this, then use convert this with the Laplace integration. Then convert the differential equation into that what we call complex transfer function. That is the system transfer function, f of p. I will show you how to get the f of p on different ways, different possibilities. And now the big advantage comes. The output of a system is O of p is now just multiplication of the input signal with the system function. That gives them the output function xo. Now the solution of the differential equation in time domain is just multiplication with two frequency functions to get the output function in. It is still a frequency function. So normally we have not a possibility to work with frequency signals. So now we go back. You see these are arrows in from time to frequency. Now we go back with inverse Laplace transformation to get the xo of t. Now this look up in the table and read in the same row the time function, and then you have solved this task. The calculation of system responses here in the frequency domain is much more easier. This is table work. I show you how to get this. This is table work. That's all. So there's a solution. I have then many years ago. I have more time in C control system lectures. Then I use a complete 90-minute lecture to solve the differential equation in a second order system. I will show you today the same solution in frequency takes not more than 10 minutes, 9 times faster. So that is the reason why we prefer, but would like to go into the frequency domain, in spite of the fact that our brain is thinking in time domain, not in frequency. Yeah? The frequency thinking is for beginners, for engineers, much more difficult than thinking in time domain. That should be very clear. Frequency domain. Okay. Some words to the system transfer function. Some people say system function, system transfer function. Three methods to get it. Maybe there are more methods, but I can tell you some information about three methods to get it. The first method is, das war der falsche Knopf. Use signal block diagrams. See chapter 2. We have done this. Yeah, if we have a differential equation system. It could not be only one differential equation, it could be a differential equation system. Draw the signal block diagram, use a reduction simplifying methods to get one block. If you have one block, then the block function is f of p. So this is the first thing. B, use known equations in phasor domain. Use known equations in phasor domain. What is this? I will explain later. And then replace j omega with p. We will do this in next step. And C is use differential equation coefficients. And then you should know the coefficients in the transfer function here are the same. You only have to know which coefficient in the differential equation goes to which position in the transfer function. See chapter 3.4. Next chapter. I will show you this way. I think we should do now a simple example and then a complicated example. Yeah. We go with a system example. I want to use a very simple first order low pass filter. Yeah? We have done in signal block diagram methods. I have the input signal U1 of t here, and I want to calculate the response U2 signal here. We have a resistance. I have to check my values. A resistor should be 1 kilo ohm and a capacitor 1 microfarad. That is given. You have just quick values, and I want to do two examples, A and B. A should be the unit step response. So our step should be 1 volt times sigma of t, and U1 of t in the second example should be a switched cosine function. Okay, so first, in case A, we need the input signal here, then we need the transfer function, and then we can calculate the output signal and reconvert into the time domain. So in both cases, we need the transfer function. So the first step is get f of p. I show you the way A and B. Method A. Use SBD. That should be B. Sorry, it should be B. SBD. So I go back to the part in my chapter 2 where we have set up the signal block diagram of this structure of the single low pass filter function. Well, I have now switched back to that part in the previous lecture where we have converted this RC first order low pass filter into a signal block diagram, and we have got this part. So I use now this element in my new lecture to calculate the transfer function. Yeah. So copy SB. The SBD plan was, I just put the both parts together. Here 1 over R, 1 over PC. I multiply these both blocks, simplifying, yeah, series connection, is 1 divided by PC times R. 1 divided by PC R, input, output, and you have a negative feedback to this position. This is U1, this is U2. That was the part chapter 2. And now we use the feedback rule to put this together and get one block with the transfer function, U1 input, U2 output, exactly that we need, and the transfer function with the rules of feedback is division line divided by 1, negative feedback, positive sign here, 1 divided by PCR here, and the same is written here. And if we put this together, multiply numerator and denominator with P times C times R, we get the final simple transfer function. 1 divided by division line, 1 plus complex frequency P times the product of capacitance times resistance. And if you do this, this is a time constant T, and T is in our size, R times C is 1 kilo ohm times 1 microfarad. And if you put this together, kilo 10 to the power of 3, micro 10 to the power of minus 6 gives 10 to the power of minus 3 gives 1 milli, and ohm times farad gives second, 1 millisecond. So we have a time constant of 1 millisecond, and the frequency function of my system is 1 divided by 1 plus P times time constant. So F is already calculated. Now we have information about this F. Later I will show you how to do this with phasor domain equations. With a voltage divider equation we also get the same result. But now I want to complete this with our step function as the input. And I think this is a good cut for the next video.